So let's talk a little bit about this new process that we found. This is the called, as we mentioned, the running maximum of the Brownian motion. And the first thing to observe is that it's non-negative. So why is that? Well, the Brownian motion starts at 0, and the running maximum records the maximal value that the Brownian motion has attained by time t. And so, right off the bat, you're at least going to be at 0. The running maximum won't record anything below 0 because, those values don't exceed 0, which is where m was at time 0. In other words, m at time 0 is 0, and it can only increase from there on. So m is an increasing process that just keeps track of the highest level that was achieved by the Brownian motion. Here, a couple of examples. You see one path right here, and right from the beginning it kind of increases, and the running maximum then stays flat while the Brownian motion kind of meanders down below. Then it moves up and starts kind of here it starts breaking its sort of past record, and then dips below again, and the running maximum stays flat, and and on and on and on. Here is another path that didn't fare as well. It spent most of its time below 0, so the running maximum stayed at 0 basically up to here, up until the time that the Brownian motion went up above 0, and then it left again, and so you have that trajectory. So the running maximum is at least 0. It's increasing, and all of the kind of the CDF and densities can be worked out from the reflection principle. So here's again a summary. Both of the CDFs. This is the CDF of the hitting time. This is the CDF of the running maximum. They're just the two are kind of just complements. So the CDF of the maximum is just 1 minus the CDF of the hitting time. The only thing to watch out for is that this is a function of b with t fixed. So the b is the actual variable that's defining the probability. So t is kept fixed, and b is the variable. And in this case, the case of the hitting time, b is fixed, and t is the variable, as it is on the probability all the way to the left there. And then taking derivatives of either leads you to the density function. And again, this is the variable here is t, it's non-negative, and here the variable is b, and it's non-negative because of this observation here. Here I just drew out what the the distribution would look like. The density of this of the maximum clearly looks like a normal random variable. In fact, that distribution is called the folded normal. So you can see how the only difference of it from the only difference it has from a normal density is this multiplying factor of 2 out in front, and that's a folded normal distribution. So you can look that up. And then from here on, there's variations on this theme. Take what's called a geometric Brownian motion. Here you have a parameter theta, and everything is raised, e to the, you take it to the exponent. So you're exponentiating the Brownian motion times some positive scalar. And then so if you obviously take a maximum of this process, the running maximum of z, that's going to be e to the theta times the running maximum of b, simply because the exponential at least with theta greater than 0 is an increasing monotone function. And you can think about what this would look like with theta less than 0. So that's be kind of similar, but there's a little bit of a trick. So you'll see if you can figure out what happens when theta is actually less than 0, so that e is a decreasing function, not an increasing function. And then all sorts of calculations are possible. You have here the moment generating function of the running maximum of the geometric Brownian motion. So this is it. And what would this look like? Well, you just integrate it against that density. This is just an example of how a calculation like this would work. Again, b is greater than 0, so I'm integrating from 0 to infinity of the the actual thing I'm taking the expectation of against the density. The dB seems to be missing here. Okay. And here what I've done is I've completed the square. I want the inside here to look something more more like a normal density, so I know, so I at least can get something familiar. And so I've completed the square, and you can check that if you expand this quadratic form here, you'll recover both this term and that term, and would pick up the one on the outside. or rather the one on the outside cancels the third term in this quadratic expansion. And what's this? This is nothing else but the standard normal evaluated at the point theta t, and this is done after a quick change of variables, x theta t minus b. So I'm replacing the square with an x, and then going through the usual dx db kind of trick, and in the end you can verify that you get this expression. So this is once again a calculation reduces to some answer times quantity that's kind of considered to be this computational unit for a lot of these problems. So often answers are expressed in terms of this this quantity here. And then finally, just show you kind of another problem that you can another example of working with running maxima. So in this you can kind of suppose that there's a two-dimensional two-dimensional area with some boundary located at 1, and so perhaps you have something starting out at this location, maybe some I don't know, some bug is crawling on a on a two-dimensional surface, and is moving towards this boundary. Maybe this is the grass or something like that, and this is all cement, and the bug is trying to get to the grass or something. You can make up your own version of this story, but suppose you're modeling this with two independent Brownian motions, and these star quantities, so x and y are both Brownian motions, with x star denoting the running maximum up to time t of x, and y star denoting the running maximum of yt. And so that is going to give you the kind of, let's suppose that dictates the position of this bug that's crawling towards the grass. So it's going to be both of these processes are increasing, so clearly it's gunning for the grass there, and so we don't know which boundary it's going to hit is the kind of the idea here. It looks like it's probably equally likely these two Brownian motions are independent, and so are the maxima, and it's equally likely for it to hit this way or this way. But you could perhaps be interested in the distribution of the shortest distance to the boundary, the shortest distance to the grass. And so you have kind of one distance here. This is the shortest distance to this edge, and this is the shortest distance to this edge here. And what's the shortest distance overall? Well, it's the minimum of the two. So 1 minus x star would be this length here, and 1 minus y star would be this length here. And now the minimum of the two is in fact the shortest distance to this boundary. So it's a little bit of a matter of how you define the boundary. If the boundary was curved, things would look, this calculation would be very different. But in this case, the closest distance to the boundary is just the minimum of these two coordinates. So now the question asks, for example, what's the distribution? We're basically trying to find out how is the distance to the boundary distributed at any point in time. You want to see kind of where we're expecting the kind of we're tracking the bug's progress, and so there's a couple of different ways. So the trick here is sort of every time you see a minimum of a bunch of variables, especially when they're independent, but it doesn't really matter if they're independent or not for the first step. Here's what you want to kind of work with. You're seeing the minimum of two variables, and you want to kind of form the cumulative distribution function, and you either will write dt is less than or equal to z, or greater than or equal to z. This would be the complement of the CDF, so maybe not exactly what I want, but I've chosen it very specifically here for a reason. This would be when is, in other words, when is the minimum greater than or equal to z? The minimum of two numbers. When is the minimum greater or equal to z? Well, it's when both of them are greater than or equal to z. So you can see how, immediately from here I get a joint probability of two independent random variables. These were two independent Brownian motions. The x star and the y star are independent, and so these two probabilities, which are equal to this one, are independent, which allows me to then talk about just one of them squared. And this would be very different if, or it would be similar, I guess, let's say I was, for whatever reason, I had a maximum here. In that case, I would compute dt less than or equal to z, because when is the maximum less than or equal to a number? It's when both are less than that number. And again, when they're independent, you could split them up and square the two together. So this is kind of the usual trick of working with minima or maxima of random variables. And so again, when you're looking at a minima, take the complement of the CDF, and then you can break it up into this form, which gives you the probability squared. So originally started as the product of these two probabilities, but because the distributions of y star and x star are the same, I've just chosen one of them, and so this one squared is sort of acting as for both. And then I've rearranged the terms a little bit. I brought over the x to the other side and the z to this side, and so you have x star minus 1 minus z. And now finally we get to the point where we can use this result here, which is the cumulative distribution function of the running maximum, which is exactly what we have here. And I just plugged it in. My 1 minus z went in for the level b up there, and the square root of t stayed. And then from here on, you can take the complement of this, right? 1 minus this will give you the CDF of the shortest distance, and you can then take a derivative to get the density, and et cetera, et cetera. So hopefully the kind of the theme of all this is clear. And in ROS, you can see the more complicated calculations that include running maximum and hitting times of Brownian motion with drift.